Hi, I'm David. I'm one of the lecturers in the Maths Learning Centre, and this is a video lecture about polynomials. It'll mainly consist of me writing on this piece of paper here and talking. It's fairly low tech, but hopefully the concepts will make sense. Alright, polynomials are a thing in mathematics that have lives as both functions and as algebra objects. And I'm going to talk about both of those things. And first I'm going to talk to them about functions. Alright. Polynomials are a kind of function. And so that means that everything that we think about functions and want to do with functions, we can do with polynomials. A function is usually a rule which takes some sort of input, like a number, does some sort of process and produces an output, like another number. And that process doesn't have to be a formula, but for polynomials it is. It can be some sort of wickedly strange thing like drawing a triangle and doing a measurement. It could be just looking up a list, but with polynomials it's a formula. So a function is a rule that takes inputs, which are usually called x, and produces outputs, which are usually called f of x. Now this notation looks like multiplication, it looks like f times x, but it's not. It's f of x, and you'll have to rely on the context that you're in to decide whether it's the name of a function or multiplying by a number. And it's not always f, it could be anything. It's tradition to use f for function, but if you're using more than one of them, they'll need different letters of their own. Okay, so for example, a polynomial is a particular kind of function that is done using a formula. So they have formulas like f of x is 2x plus 3, or f of x, for example, f of x is 2x plus 3, or for example, f of x is x squared minus 5x plus 7, or f of x is x to the 5 minus 6x to the 9 plus a half of x to the 3 plus root 2x minus 8. Anything that has powers of x and those are multiplied by numbers and added together, that's a polynomial. We don't normally see ones with irrational numbers like this as part of the coefficients, but it's technically not impossible. So I wanted to put it there. And most often we'll see them with whole numbers because that's what polynomials were when they were first invented. But they are allowed to have fractions in them too. And the general form of writing this that most people write is this. A0 plus a1x plus a2x squared plus, and then some number of things, an x to the power of n. I've written this in the reverse order to these two actually, but this is how it's normally done. And so this a sub 0 is just the name of a number that we don't know what that number is, and normally you would put numbers in those positions. So in this case the 3 is a0, and this 7 is a0, and this minus 8 is a0, because it's just a plain number. And then a1 is the number that's next to the x, it's called a coefficient, and then an x to the power of n, well, that's the biggest one. So in this case, this n is 1, and this n is 2, and this n is 9. That's the biggest power. They don't have to be written in the same order as this. Okay. So these things here are called coefficients. Okay, that's what a polynomial is, and they tend to look like this. And polynomials are nice because they're the easiest to calculate, and they're the easiest to teach a computer to calculate, and there are some really nice connections between the algebra and the shape of the graphs of these functions. Which I should probably mention. Graphs of functions are a really important way of understanding them. So what we can do is we can make a big list of all the x's that we could put in and the matching function values, that's what these are called, that come out, and we can interpret the x as an x coordinate and the function value as a y coordinate and draw a graph that way. So you can put x here, you can put a y here, and what we can say is that the y value is some function of x. And so we can say, well, when x is 0, it's this. When x is 1, it's this. When x is 2, it's this. When x is 3, it's this. When x is 4, it's this. When x is 5, it's this. And everything in between also have answers too. And they're allowed to be negative numbers. And technically the whole thing goes on forever. And so they might look something like this. Each of these heights or depths is calculated by subbing in values into the formula. And it turns out that we don't actually have to sub in all those different values to figure out what the graph is. We can use some of the features of just the way the algebra is written to know what the graph is like. Okay. So this is called the graph of the function. Okay, so I'm going to talk about various different features of this graph and talk about various different features of the function and make sense of how these things are related. Okay. So let's see. Well, the first thing that I've already mentioned is that every point is made from subbing in an x and figuring out a matching function value, which is the y. And so that means that if we know the function that the graph passes through certain points, then it's possible to figure out what the formula is. And I'm going to do an example of that just to show you. So the first thing is points on the graph. Okay, so for example, if f of x is equal to 2x, not 2x, sorry, getting ahead of myself. If f of x is equal to a0 plus a1x plus a2x squared, and f of 0 is 3, f of 1 is 2, and f of 2 is 9, find a0 and a1 and a2. So if you have some information about what polynomial you have, you can figure out which one it is based entirely on the function values. So this means that when I sub in x, the answer should come out to 3. When I sub in 1, the answer should, sub in 0 for x, the answer should come out to 3. Sub in 1, the answer should come out to 2. Sub in 2, the answer should come out to 9. And so I can figure out what all these coefficients are. So I know that f of 0 is this. That's what I get when I put 0 into the formula. And that comes out to the answer just a0. But f of 0 was supposed to be 3, and so therefore a0 is 3. Okay? So actually f of x is 3 plus a1x plus a2x squared. And now we could know that f of 1 is 3 plus 1 times x plus 1 times, not paying attention. I'm replacing the x with 1 plus a1 times 1 plus a2 times 1 squared, which is 3 plus a1 plus a2. But f of 1 is supposed to be 2, so 3 plus a1 plus a2 is 2, which means that a1 plus a2 must be negative 1. Alright, well I wasn't able to figure out what a1 and a2 were there, but I can maybe set up another equation from the other value of f that I have. F of 2 is 3 plus a1 times 2 plus a2 times 2 squared, and so that's 3 plus 2a1 plus 4a2, which is supposed to be 9. So we get that 3 plus 2a1 plus 4a2 is 9. So 2a1 plus 4a2 is supposed to be 6 if I subtract 3 from both parts of this equation. And I notice that they're all even, so I can divide by 2 like that. So somehow I have to figure out what a1 and a2 are, and I can do that. If I call this equation 1 and this equation 2, I can do equation 1, equation 2 minus equation 1 is this minus that. So a1 minus a1 is 0, 2a2 minus a2 is a2, 3 minus minus 1 is 4, so a2 is 4. And then if I sub that back into number 1, I can have that a1 plus a2 was minus 1, so a1 plus 4 is minus 1, which means that a1 is minus 5. And so actually f of x is a0, which was 3, plus a1, which was minus 5, x, plus a2, which was 4x squared. So the point of this example was twofold. It was to show you that it's possible to use the fact that f comes out to certain values at certain places to figure out some stuff about the formula. But more importantly, it was also about how to set out some of your working. Okay, I've been very careful to use some nice connecting words between things. When I've done f of 1, I've done it's equal to this, and then f of 1 is still equal to this, so I don't have to have anything in front of it. And when I've solved equations, I haven't put equal signs over this side. So there's lots of different bits of mathematical working that you can see here. Okay, so that was an example of using points on the graph. There are some very special points on the graph that we need to mention, which are the y-intercept and the x-intercepts. So the y-intercept is the place where the graph crosses the y-axis. And it's important when you're drawing a rough sketch of something like this to be able to find out where it is. I might put a box around things actually. So the y-intercept is where the graph cuts the y-axis. and the place where the graph cuts the y-axis lines up with 0 on the x-axis. And so that means that if I put 0 into the formula, it should come out to whatever this number is. And so what that means is that it's also the y-intercept is f of 0. The y-intercept of the graph y equals f of x is the number f of 0. And that's always true. And so if you want to find the y-intercept of something, you can just sub in 0 and see what you get. So e.g. find the y-intercept of, I'm going to give it a different name today. X squared minus x plus 3. Well, the y-intercept is g of 0, which is 0 squared minus 0 plus 3, which is 3. So that means that when I draw the graph, it will cross the y-axis at the place where y is 3. The next important thing to talk about is x-intercepts. The x-intercepts are the places where the graph crosses the x-axis. And they are also, well, let's have a look at this. The places where the graph crosses the x-axis, well, they line up with 0 on the y-axis. So they are the places that when I sub it into the formula, the answer I get is 0. Because if I sub this into the formula, I get that height, and this into the formula, I get that depth. This into the formula, I get 0 as the answer, so I don't move. So if you want to find the x-intercepts, you need to find the places where f of x equals 0. Okay. If it's called f, of course. It might not be f, it might be g or p or something else. Now, functions generally, before we invented graphs, well actually it was the other way around, we invented graphs first and then functions, but functions don't have to have a graph that we're capable of drawing. There might be some other description of how this thing is working. And so functions have a name for this when you're not talking about graphs. When you're talking about the graph, it's called the x-intercept, and when you're talking about the function just as a formula, it's called a 0 of the function. Numbers x with f of x equals 0, zeros of f. And so you'll find that when people who teach mathematics talk about x-intercepts, sometimes they say zeros, sometimes they mean x-intercepts, and they really mean the same thing. It's just that zeros is talking about the function itself, the formula, and x-intercepts is talking about the graph. Okay. So, how might you do this? So let me do an example first, and then I'll do a more complicated example in a second. Find the x-intercepts of f of x equals 3x plus 7. And so what that means is I need to solve the equation f of x equals 0. which would be 3x plus 7 equals 0, which would be 3x equals minus 7, which would be x equals minus 7 over 3. So you can say the x-intercepts is when x equals minus 7 over 3. But you could also say, if you wanted, just while you're at it, minus 7 over 3 is the 0 of f. Okay, this one only had one 0. One place where the function was 0, it only had one x-intercept, one place where the function crosses the x-axis. So, that's that. But what if it was more complicated than that? It can be a bit tricky to figure this out. And this is where we need to delve into a little bit of algebra. It turns out that if you were able to write your function as a multiplication of things, then the only way to multiply things to get 0 is for one of them to be 0. So you can factorize it, and once it's fully factorized, you can know what the zeros are. To find the zeros or x-intercepts, we need to factorize the polynomial. Okay, so factorize means to write with factors, and a factor is a piece that multiplies together to produce something bigger. So let me do an example. Find the zeros of p of x, which is x squared minus 9. Okay. So we need to solve p of x equals 0 to find the zeros, which means we need x squared minus 9 equals 0. Now, I could totally solve that without factorizing, right? I could do this, and when you square root 9 you get 3, but it could also be a minus 3, and so I get the zeros are x equals 3 and minus 3. So you could have done it that way, but alternatively, without actually setting it equal to 0 first, I could have factorized the original function. So I could have done this, or p of x is x squared minus 9, and that's a difference of two squares, which means it must be x minus 3, x plus 3. And in order for me to solve the equation p of x equals 0, well, I need one of those two things to be equal to 0. So p of x equals 0, which means I need x minus 3, x plus 3 to be 0, which means either x minus 3 is 0 or x plus 3 is 0, which means I get x equals 3 or x equals minus 3. So the zeros are x equals 3 or minus 3. But here's the thing. Some things it's possible for me to do it this way, and that's fine, and that's probably quicker. But this means that technically we don't even need to do this solving part, because every time the zeros will come out to be minus the numbers that are here next to the negatives. So, one more example. Find the x-intercepts of h of x, just going to give myself a bit more space, h of x is x minus 5, x minus 3, x plus 2. Now I know that if I did my algebra and expanded out all those brackets, it would be a polynomial. But I don't care. I don't care about what that is, because I can tell what the x-intercepts are directly from this. Okay? I know that if I made this equal to 0, then each of these, one of them had to be 0, at least one. And so that would mean that the only way for x minus 5 to be 0 would be if x was 5. And the only way for x minus 3 to be 0 would be if x was 3. And the only way for x plus 2 to be 0 would be if x was minus 2. And so I take the numbers that are here and I do the minus of them, and that will produce the correct zeros. The zeros of h are 5 and 3 and minus 2. Therefore, the x-intercepts are x equals 5 and 3 and minus 2. And I can read that directly from this version here. Now the tricky bit is sometimes managing to write it as factors that way, to factorize it. There are methods for doing it for quadratic equations. I'm sure you can go and look up that in any, I think it's in year 10 or 9 in Australia. Maths, you can go and look up how to do that. And it becomes trickier the higher the number of x's that there are involved. Okay, so far we've talked about just general points on the graph. We've talked about the y-intercept, and we've talked about the x-intercepts. And what that has meant is that we've needed to talk about factors here. I'll get back to factors again later. Okay, so that's not all that much that we can get about our graph. I mean, at the moment, the pieces of the graph that I've talked about are just this point, this point, this point, this point, and this point. And that's not nearly enough to really get a handle on what's going on. And some of these graphs may not even meet the x-axis at all. And that can be a problem. So we'd like to know a little bit more about what they are. And unfortunately, in this topic that I'm doing today, we're not going to get to some of the nitty-gritty of figuring out all the details here. So for example, it would be very nice to know where these turning points were. But that's not going to be covered today. This turning point, I can get a handle on that actually. I'll be able to see that one. But I'm not going to be able to tell exactly where they are with just the tools that I tell you today. But what I will be able to do is give some general information, a little bit about, just from the information we have, how to tell what's going on in the rest of the graph. So, we've talked about some various points. Any point on the graph can give you some information. Using the formula, I can figure out every point on the graph. And the x-intercept and the y-intercepts are when things turn out to be either you put in 0 for the y-intercept or you get out 0 for the x-intercepts. Now I'd like a little bit more about those turning points and the general shape of the graph. I can get the shape of the graph, the general shape of the graph, and roughly how many turning points it should have directly from one piece of information about the graph, which is the highest power you see. So I'm going to just say shape and number of turning points. Okay, and you get that directly, just general information about how it might go, directly from the highest power. Okay, so the highest exponent as in the highest number that is x to the power of that number, tells you how many there should be, and it's called a degree. We need a name for it because it's going to become important in a second. So for example, f of x equals x cubed plus 2x squared minus x to the 6 has degree 6 because the highest power of x is x to the power of 6. Okay, so the highest power is called the degree, and it turns out that the number of turning points can be at most one less than the degree. And it also turns out that if you have an even degree, then both ends of the graph point in the same direction, and if you have an odd degree, then the two ends of the graph point in opposite directions. So that's quite a bit of information. I'm just going to pop that down. So the first piece of information is if the degree is even, then both ends of the graph point the same way. So what that means is, just in terms of pictures, if it's got an even degree, they're either both going to point up, or they might both point down, or they'll both point up, or they'll both point down. That's regardless of how many turning points it has. If it's got an even degree, both ends have to point up. And the reason for that is that if I put a negative number into x to the power of 6, just ignoring all the rest, minus number to the power of 6, well, a negative number to an even power is always positive. Even powers always produce positive answers. And so that means if you have something like x to the power of 6, then even when you put negatives, you get big positive answers, and when you put a big positive number in, you get a big positive answer. And so the graph will go up because you get positive answers over this side, and up because you get positive answers over this side. If I'm doing a minus x to the 6, well, it'll be more like this, because you'll get a positive answer and then minus, so it'll be negative. So the two ends point in the same direction if it's an even degree, but they point in opposite directions if it's an odd degree. So if the degree is odd, then both ends of the graph point the opposite way. So you might have something like that, where one end points down and one end points up, or you might have something like this, where one end points up and the other end points down, or even a straight line does that job. One end points down and one end points up. So if the degree is odd, the highest power is an odd number, it's going to be opposite directions, and if the highest power is an even number, it's going to be same direction. What I haven't got to is how many of these turning points it's capable of having. So those were two very important pieces of information. They deserve to be in boxes. Okay. So the other piece of information is that the most number of turning points you can have is one less than the degree. And the number of turning points you can have, if you have an even degree, you can have an odd number of turning points, and for an odd degree you can have an even number of turning points. And so if the degree is n, there are at most n minus 1 turning points. Okay, and in fact, The number of turning points could be any number up to n minus 1, but they skip. All right? So those are the 3 bits of information that we have at the moment, just from whatever the highest power is. So the fact that this is x to the power of 6 means that I know both ends point the same way, and I know that it can have at most 5 turning points. It could have 1, it could have 3, it could have 5 turning points. So for this has 1, this one has 3, 1, 2, 3, 4, this one has 5. These are all the options for the shape that this could be. Now there is one more piece of information that will tell me about which way up it is. So you'll notice that these even ones go up, down, up, and these ones sort of go north, east, southwest and northeast, or if you like, up going to the right, down going to the right, or up going to the right. So how do you decide which of those it is? And you can decide that purely and completely based on what number is next to the highest power. What is the coefficient of the highest power? And so the orientation if the coefficient of the highest power is positive, the right-hand end will point up. If it's negative, the right-hand end will point down. So in this case, this x to the power of minus x to the power of 6, because that's a negative number next to the x to the power of 6, the right-hand end is going to have to point down, so it can't be either of these. It would have to be this one, or it could be this one, but up the other way. Okay. So, some examples would be useful. I'm just going to clarify this one more time, just to draw a picture of how this might look. So for degree 2, it will either look this way with a negative number as the biggest coefficient of x squared. So this will be minus something x squared plus bx plus c. And this way for minus, for plus something x squared plus bx plus c. And this is a bit sloppy the way I've written it here, because technically if I just wrote the letter A without telling you what it is, it could be positive or negative. And if it was already negative, then minus it would turn it into a positive. Degree 3, I should tell you that a degree 2 is called a quadratic. Degree 3, which is called a cubic, will look like this. But it may actually not have 2 turning points. It may look just like that. It might not have any turning points at all. Or it could look like this coming down, and again it might not have any turning points at all. So that's what cubics tend to look like. And degree 4, which is called a quartic, could be like that. It could be like that. And that's got 3 turning points, 1, 2, 3, and that's the most that it can have. It could also only have 1 turning point. Something like that. Or like this. These are all okay with degree 4. Once you get up to degree 5, I believe it's called a quintic, but most people don't actually use the word, you just say a degree 5 polynomial. You start to have even more options for what could happen. So in a degree 5 you could have up to 5, no, that's an even ordered one. In a degree 5 you could have that, or it could be that, or you could have just 2, or even just 1. So these are all the options for degree 5. And the higher the degree you get, the more options there are. It's much more likely to have all the turning points than it is to have not all the turning points. So all of this information together is enough information to have a handle on what you think this is supposed to be like. But there is one more thing that can give us just a little bit extra, and it's to do with how you factorize it. But before I get to that, I am just going to do an example. For example, no, I'm not. I'm going to come back to that in a minute. So there's one more piece of information that we might need, which is, sure, we can figure out what the X-intercepts are just here by factorizing, but it would be cool to know how it met the x-axis. Like, is it going to bounce off, like having turning point on the x-axis, or is it going to just meet cross through the x-axis? And that information is to do with the powers that go on those factors. So, a higher power on a factor will cause it to look like, if you're very close, one of those other curves. So, the way it meets the x-axis it's really hard to describe. Powers of factors change the way it meets the x-axis. So it's best to do it as an example. If you have something like x minus a squared and just other stuff, then what will happen is that your graph will do something like that. Here is the point A. It certainly meets the x-axis at the point A, but what it's going to do is it's going to have a turning point there. And that'll happen for anything where there's an even power. Alright, so that's a pretty scrappy thing that I just wrote. So x minus a to the n for n even indicates a turning point on the x-axis at x equals a. But if you have x minus a to the n for n odd, then that indicates that it passes through the x-axis at x equals a. The reason that works is that if you're extremely close to x equals a, then all of these other factors aren't really going to be all that different if you move a little bit closer to x equals a. So if you're a little bit less than a, then this bit will be negative, but when you square it becomes positive anyway. And if you're a little bit more than a, when this bit is negative, this bit is positive, so it comes out to be positive. And so these bits here aren't going to change if you're not near their zeros. And so it'll be positive on both sides, and so it's going to come down and come back up again. Only it might be negative on both sides as well. So all of this information together can allow us to draw a sketch of a graph, a rough sketch. You don't have to be exact about it, just based on the way that the function is written. So now I'll do an example. Sketch a graph of f of x, which is equal to 3x minus 1 squared, x plus 2. Okay, so if I'm going to do that, you don't even need to properly describe what's going on, but I will. So I notice that this has got an x minus 1 squared. If I did some algebra, I would get an x squared in there, and then multiplying that by this, I'll get an x cubed. It's going to have a degree 3. It's going to be a cubic. And I know the possible shapes of a cubic. They're generally going to be this way or this way. And I also know if I expand this all out, then the x cubed is going to come from this, and that's going to get multiplied by 3. So the coefficient of the x cubed is going to be positive. Sorry for the building works upstairs. I wasn't expecting that to happen. Okay, so it's a degree 3, which means we know what shape it is. We know the coefficient of the highest power is positive. Which means it's actually this way, because the right hand end will be pointing up. And we also know the zeros are 1 and negative 2, because this factor has a minus 1, so it's plus 1. This factor has a plus 2, so it's minus 2. And we also know it has a turning point on the x-axis at x equals 1. And that's enough information to get a rough idea of what the graph should look like. So there's negative 2 and there's 1. Probably don't need this stuff. And it's going to turn on the x-axis at 1 and go through the x-axis at minus 2, and it's going to be up this way. If that 3 had been a minus 3, it would have gone this way. And that's enough. It is possible to figure out what this point is. I'll just do that. Y-intercept is given by f of 0, which is 3 times 0 minus 1 squared, 0 plus 2, which is 3 times... Now minus 1 squared is 1, which is 6, and so this point here is 6. When you're just asked for a sketch, it doesn't have to be drawn to scale. And so this is a good enough sketch that gives all the information that we need. And you can do this same process in reverse. Find a formula for the polynomial px with this graph. Yep, and I'm going to give you 1 point on this graph. I might just make this a bit taller. and this is going to be the point 350. And I'm going to pop maybe 1 here, minus 2 here, 4 here, and 5 here. Okay, so here's a graph, and I should be able to make a good guess at what the function's going to be. So, let's see, we can see the zeros. So, the zeros are minus 2, 1, but it has a turning point there. And 4 and 5, it has a turning point there too. Okay. When I have a look at it, let's just see there's 1, 2, 3, 4, 5 turning points, which means it could be a degree 6 polynomial. A degree 6 polynomial can have up to 5 turning points. 5 turning points, which usually means degree 6. And we've got a confirmation here actually. Both ends are pointing the same way, which means it should have even degree, so that's pretty good. Okay. All right, so this is pretty good. We've got quite a bit of information here. So I'm thinking that px, because of the 0 at minus 2, it should have an x plus 2. Because of the turning point at 1, it should have x minus 1 squared. Because of the 0 at 4, it should have an x minus 4. And because of the turning point at 5, it should have x minus 5 squared. Now let's just count. If I expand this all out, I'll get 1x here, an x squared here, an x here, and an x squared here. X times x squared is x cubed, times x is x to the 5, times x squared is x to the 6. Okay, it has the correct degree. But, like the one I had before had a number multiplied out the front. Well, there's nothing stopping me from having a number here. I just don't know what it is yet. So I'm just going to do this for some number a, but I don't know what that number is yet. I'm just going to go looking to see if I have enough information. Ooh, I do have a point that is on the curve. That's useful. So if I have a point on the curve, I can use it to calculate this missing a, because I know that if I put 3 into this formula, it should come out to the answer 50. If I didn't have a point on the curve, I would never know what a is, and I would just have to leave it like that. But I can know already that this a is going to have to be negative because it's both pointing downwards. And so I do know that okay. So since they're both pointing downwards, so we also know that P of 3 should be 50. Let me just check that my drawing. Yep, okay. So P of 3 should be 50, and so let's see. P of 3 is a times 3 plus 2, 3 minus 1 squared, 3 minus 4, 3 minus 5 squared, which is a times 5 times 2 squared times minus 1 times minus 2 squared, which is a times 5 times 4 times minus 1 times 4, because minus 2 squared is still 4, and 5 times 4 times 4, well 5 times 4 would be 20, So that'll be 80. Yeah. But it's minus 80a. And this is supposed to be 50. And so I can divide both sides by this minus 80, which means I'm getting minus 5/8. So it's traditional to put the minus out the front, and I can divide both of them by 10. And so therefore, P of x is actually minus 5/8 times x plus 2 times x minus 1 squared times x minus 4 times x minus 5 squared. Okay. Cool. So I can use all the information I know about the shapes of these graphs to have a good picture of how the formula is related to the graph. Okay, but there were some things going on here that were interesting from an algebra point of view. So mathematicians are interested in the relationship, in graphing things and figuring out answers to stuff. But we're also interested in how things relate to each other and how they behave. Now, we've spent a lot of time thinking about how numbers behave. We know certain rules about how expanding multiplications when there's additions around. We know rules about how powers behave and how to rewrite things. We know that every number has a number that you can multiply it by to get 1, and those sorts of things. And those are algebra things, things about the behaviour of numbers. And what we have here is something that in many ways is like a number, but isn't quite, because it's it's a formula that works for lots of numbers all at once. So what I can do is I can think about them as objects in their own right that I can multiply and add and do stuff to. So I've already seen this here. Back here, I was able to think of the polynomial x squared minus 9 as the same as what you get when you multiply these two polynomials together. Okay? And it turns out that we don't even need, if we have something in this format, we don't even need to expand it out to have any idea of what it looks like. We can leave it in this format, and that's most of the information we need. Later on, it might be useful to expand it out. So I'm just going to write a title. Polynomials as algebra objects. So it turns out that we can think of them as algebra objects and have operations that do addition and multiplication and subtraction and those sorts of things, and hopefully division. Division is going to be a bit tricky. So you can add, subtract, multiply, and divide polynomials. To create new polynomials. So adding them and subtracting them and multiplying them, we're used to that from the algebra that we've learned in the past. So just for example, if P of x is x plus 3 and Q of x is x squared plus 2x plus minus, give me a second. (15), then P of x plus Q of x is the same as, well, that p of x is x plus 3 and the q of x is x squared plus 2x minus 15. And so when we add them, the x squared doesn't have any other x squareds to add to, it's still b there. The 2x can add to this x to give us 3x, and the minus 15 can add to the 3 to give me minus 12. Ta-da! I mean, it's not particularly edifying, but it's a thing you can do. And this itself is a new polynomial. So two polynomials, when you add them together, still a polynomial. Px minus qx, well, let's see, that would be x plus 3 minus, and this entire thing is going to have to be subtracted. Which means I need a minus outside all of it so that I know that it all belongs to that minus. And I do know with algebra that subtracting all these things that are added together means subtracting the things that are added and adding the things that are subtracted. So I can do that. Now that minus x squared doesn't have anything to belong to. X minus 2x is minus x, and 3 plus 15 is 18. And so that's what I get there. And if we multiply them together, don't forget that sometimes mathematicians use a dot for times, where, especially when there's x's around, so that you don't get it confused with the x. Well, we'll do what we always do with multiplying, and we'll use the distributive law, which says that this can multiply by each of those things, but then each of those things can multiply by the x plus 3. So it turns out that we can multiply this by each of those and then this by each of those, and that should be the answer. So x times x squared is x cubed, x times 2x is 2x squared, x times minus 15 is minus 15x, and 3 times x squared is 3x squared, and 3 times 2x is 6x, and 3 times minus 15 is minus 45. Oh, and I wish I had given myself a tiny bit more space so that I could do this. I reckon I can just fit it in here. We have an x cubed, we have 2x cubed plus squared plus 5x squared plus 3x squared, which is 5x squared, minus 15 plus 6 is minus 9x minus 45. Okay, so you can do it, right? This is the expanded out version. This would be a perfectly good answer, and if I could factorize this, I would actually even know what the zeros and what shape this graph would be, actually, if I drew it as a graph. So I can always go back to the graph version if I like. So the hard thing is the division. Now, here's the thing. If you knew that you had a polynomial, and you knew that it was created by doing x plus 3 times something, the question is, how would you know what that something was? So the big problem is this. If you knew that you had something, if you knew that this thing was something times x plus 3, how would you figure out what the something is? Okay, so what we have is a process, well, we need to find a process for polynomial division. And there are several ways of doing this, but what some people have created is an algorithm that does the job. You're able to figure this out in any way you like, so I'm going to show you two possible ways of doing this. So let me just do an example that says that this divided by that comes out to this, as it should be if the multiplication works properly. Let's do this division. Okay, so I know that the answer is going to come out to x squared plus 2x minus 15. because these two things multiply to give that. And multiplication is the opposite of division, so it should work. But I need a way of figuring this out. So one way to figure it out is just to imagine, so we need a QX so that this is equal to x minus 3 times QX. And so we can try and just slowly figure out what the QX has to be, a little bit like a Sudoku. And what some people do is that they do that, the expanding out, similar to the way I did it before. I know that if I'm going to achieve an x cubed, this QX is going to have an x squared, and so I can do this. Something x squared, something x and a constant. And I know that when I expand this out, I'm going to get something x cubed, something x squared, and something x. And then this 3 is going to be, well, it's going to be a 3 times x squared, which is a something x squared. It's going to be a 3 times an x. So that's a, well, times something x, it's going to have an x there. And 3 times a constant is going to be a constant here. All of these things are going to need to have numbers put in them. And I'm just going to put some spaces. Okay. Now, here's the thing. If x plus 3 times this is going to come out to 1x cubed, this is going to have to be a 1 here and here. Which means this is going to be a 3 times 1, which is 3. Now, just a second, these two are going to have to add together to give 5x squared, so this would have to be a 2. And if this is a 2, then that has to be a 2 because this came from x times 2x. But if this is a 2, 3 times 2x would be 6x, and so we can figure out this one. But these two have to add up to minus 9x. And so I'm going to need a minus 15 here, or it's not going to come out to minus 9. And if that's a minus 15, this came from x times this one, so this would have to be minus 15. And then finally, just to make sure it's working, the 3 times the minus 15 should be minus 45. And that does indeed work out to x cubed plus 5x squared plus minus 9x minus 45. And so therefore, x cubed plus 5x squared minus 9x minus 45 divided by x plus 3 must be x squared plus 2x minus 15. So that's one way of doing it. And it's a perfectly acceptable way of doing your working. You have definitely shown that when you do this times this, it comes out to the answer. And so if you multiply things and you get an answer, then when you divide them the other way around, it should also work. That seemed a little bit like, jiggery pokery. And what some people prefer is a method that is a little more precise, where you follow through a procedure and it gives you the answer. And that's called the polynomial long division process. So I'm going to do that same one again with the polynomial long division process. And it's actually going to do the same job that we did, but by following a procedure over and over. So we can go or polynomial long division. So the way polynomial long division works is it's designed to do the same job we did here. First we're going to figure out what this number is. Then we're going to figure out what this number is. And then we're going to figure out what this number is. Then we're going to figure out what this number is. Then we're going to figure out what this number is. And then we're going to figure out what this number is. So we're going to do them all in that order. And the way we're going to do it is with division. So I know, just watch back here, that that the x cubed divided by the x has to be this. We knew that this times this had to be x cubed, so if I go x cubed divided by x, it should give me a single x squared. And then I knew that 3 times this had to produce this, and then we had to figure out how much was left to match up to the 5 that we were going for. So when you figure out how much is left, that's essentially a subtraction. So what we can do is do this by doing division and multiplication and subtraction. So here we go. So we write the thing that's on the top of the fraction under this division symbol. Okay. This isn't a square root, it's a division sign. And then we're going to do divide, multiply, subtract. So we're going to do the biggest power we see divided by the biggest power here, and x cubed divided by x is x squared. And then what we're going to do is going to go 3 times x squared. And we're going to... wait. We're not going to do the 3 times x squared. That's going to happen. We're actually going to do the x squared times all of this. So x squared times this is x cubed plus 3x squared. And we're going to take that off. So x cubed minus x cubed is 0, as it should be. 5x squared minus 3x squared is 2x squared. Minus 9x minus nothing is minus 9x. Minus 45 minus nothing is minus 45. And now we're going to ignore everything we've seen so far and do it again. So, 2x squared, and I'm going to cover this up too, don't need that either. 2x squared minus 9x minus 45, so we'll look at the first power. 2x squared divided by x is 2x. And then we'll go 2x times this is 2x squared plus 6x, and then we'll take that off. So 2x squared minus 2x squared is 0, that was the whole idea. Minus 9x minus another 6x is minus 15x. Minus 45 minus nothing is minus 45. And then I will go minus 15x divided by x is minus 15. And then minus 15 times this is minus 15x minus 45. And then we'll take that off and we're going to get nothing left. So there's nothing left to do. And therefore it turns out that this divided by this is equal to that. Okay, that's the polynomial division process. Now, here's the thing. When we first learned division, and we did division with plain old numbers, it turned out that not every number could be divided by every other number. So I know, for example, that 21 divided by 3 is 7, but 22 divided by 3 is 7 and a bit. And the same thing's going to happen with polynomials. Sometimes polynomials aren't going to go into other polynomials. And that's going to be an issue. So what we're going to have to do is we're going to have to say, all right, just like with 22 divided by 3, I can go, well, 22 is 1 more than 21, and 21 divided by 3 is 7. So 22 is 3 lots of 7, well, 7 lots of 3, and 1 left over. That's what we're going to do. We're going to have remainders. And so we're going to start thinking about division as actually attempting to solve a multiplication problem. So it may be no, I'm not going to write that. So it turns out that with any polynomial you like, and any other polynomial of smaller degree, or possibly even equal degree, you can always write one of them as something times the other, but there might be a bit left over. So any polynomial px and any polynomial I shall call it dx of smaller degree than p it's always possible to write px is dx times something plus a little bit left over. And this little bit left over will definitely have properly smaller degree than the d. Now, I mean, that is the theorem, it's the truth. There's a lot going on there, but the idea is that we're going to attempt to write px as dx times qx. We're going to attempt to go px divided by dx is qx, but we might not be able to do exactly. There might be a little bit left over, and that little bit has to be smaller than the thing we're dividing by. So when I divide by 3, the only remainders I can possibly get left over is 0, 1 or 2. Same deal, if I divide by x plus 3, the only remainders I can possibly get are whole numbers. Well, not whole numbers, but plain numbers without x's in them. And it's easier to do this as an example, and it's easier to do this with polynomial division. What it turns out with is that you can always keep doing this polynomial division as you go, keep going, keep going, keep going, keep going, keep going. And at some point, it may be that you're not going to be able to divide the thing that you get by x. Now, as us, it got a 0, so you don't need to divide it by x. But it may be that this number here, this minus 45, didn't match this minus 45, and there'd be a number left over. And you can't divide that number by x, and so you stop. And that's the remainder. And so we call it r here because it's the remainder. So I'm just going to do some terminology. In this thing here, this is called the quotient, and this is called the remainder. Okay. So, it's best to do this as an example. And you don't have to do it with a little thing here that just has x instead of an x squared. It can be done with higher powers as well. And I might do both examples just to make sure that you know what's going on there. Maybe not. Might not have time to do that. But let me just do an example. So find the quotient and remainder when x to the 5 minus 6x squared plus 7 is divided by x minus 3. Okay. So we're going to do a polynomial division. We're going to do this divided by that. So we're going to imagine it as a fraction with this on the top and this on the bottom, because divided by means that the thing after divided by goes on the bottom. And so we're going to get x minus 3 now, I notice that this has got an x to the 5, but doesn't have an x to the 4 or an x to the 3, and it doesn't have an x. It's going to be easier on me if I make a bit of space, because I'm going to need to fit them all in eventually. So I don't have any x to the 4s, and I don't have any x to the 3s, and I don't have any x's. Okay. So x to the 5 divided by x is x to the 4, and then I'll go x to the 4 times this is x to the 5 minus 3x to the 4, and I'll take that off. So x to the 5 minus x to the 5 is nothing. 0x to the 4 minus 3x to the 4 is plus 3x to the 4. This didn't change because I didn't subtract anything off of it. Okay, so now I'll do it again. 3x to the power of 4 divided by x is 3x cubed. I'll multiply this by that. So I got 3x cubed minus 9x, sorry, 3x to the 4 because I times it by x, minus 9x cubed. Good thing I caught that. And that's what I've got. And I take that off and I get, that's nothing, minus 9 will give me plus 9. So 9x cubed divided by x would be 9x squared. Multiply this by that gives me a 9x squared cubed. 9x squared times x is x, 9x cubed. 9x squared times minus 3 would be minus 27x squared. Let's take that off. And so we've got 9x cubed minus 9x cubed is 0. Minus 6x squared minus 27x squared is 21x squared. We're going to run out of space, I'm sorry. So 21x squared divided by x is 21x. Multiply that by that, 21x squared. 21x times minus 3 is minus 63x. Take that off. We've got 63x plus 7. Oh, so sad that we ran out of space. So 63x plus 7. 63x divided by x is 63. I've just written that up here. 63 times x is 63x. 63 times minus 3 would be 189. Take that off. 7 minus 189 is 7 plus 189, which would be 196. And let's just see, 196 divided by x. No, there are no x's there to divide. I mean, I could totally do 196 over x, but that would turn into things that aren't polynomials anymore, and so I'm just going to stop there. And so it turns out that the quotient is what I get on the top here, x to the 4 plus 3x cubed plus 9x squared plus 21x plus 63, and the remainder is 196. And it's totally okay for the remainder to be a wickedly huge number. Okay, and just to be sure we know what's going on, x to the 5 minus 6x cubed, x squared, sorry, plus 7 should be equal to x minus 3 times x to the 4 plus 3x cubed plus 9x squared plus 21x plus 63. And then we'll need to add a 196 to get it to come out to the right answer. That's how it works. If I really, really wanted to do it as a division, I could divide by the x minus 3. Oh, I've written 121x here, sorry. And it would look like that. And that's fine too. But just remember the remainder is the 196, not the 196 divided by x minus 3. And that's polynomial division. At the moment you're going, well, what does that achieve, David? It's like, well, I mean, really at the moment I'm just thinking algebra-wise. I'm going, well, this is a thing I could totally do. Now there is one last thing to tell you, which is kind of cool. And it's something that sort of relates this polynomial division back to the polynomial being a function. So at the moment this polynomial division is just a thing that we can do with polynomials as algebra things. And we're really just seeing them as strings of x's and numbers and they're just sort of there. But if we think about it being a function again, then I can notice something kind of cool. If I sub in x equals 3 into this, I'll get 3 minus 3 times whatever this works out to be, which is 0 times this, and so I'm going to get 196. Which means that if I sub x equals 3 into this, that's the same answer as subbing x minus 3 into x equals 3 into this, which means that I'm going to get 196. And that's going to happen every time. If I divide by x minus something, and I sub that something into the function, then whatever the number is at the end has to be the remainder. And that's called the remainder theorem. So we can say if px is divided by x minus a, then p of a is the remainder. And what that does is it gives us one way to at least check at least one part of our answer. Now we could totally check the full answer by actually multiplying this all out and seeing if it did come to x to the 5 minus 6x squared plus 7, and that would check our own answer. But it might be a little easier to just try and check if the number 196 is correct. Okay, so e.g. from above, x to the 5 minus 6x squared plus 7 divided by x minus 3 should have remainder 3 to the 5 minus 6 times 3 squared plus 7. 3 to the 5 is a pretty big number. I'm just going to get a calculator for this. You can tell I don't use this calculator very often. I couldn't even get the lid off. So, what was it? 3 to the power of 5. Whoops. 3. Where's my powers? Power of 5 minus 6 times 3 squared plus 7 is 196. And so I've at least got the remainder right. But this matches very neatly all the way back to when we were factorising things. We know that when we sub in x equals 3 into this, it comes out to 0, then px comes out to 0, and that means that I could factorise it to have an x minus 3. But being able to factorise it is the same as being able to divide it, being able to write it as a multiplication, which means the remainder should be 0. So that means that I can actually factorise things by trying to guess what the 0 is going to be. And I know that the zeros are what I get when I sub things in. So just one final example before I sign this off. Give me a second. Factorise this. X cubed plus 2x squared plus 1. No, just a second. minus 1, sorry. Okay, so being an x cubed, I should be able to factorise it to have something with x, another something with x, another something with x. And so one way of trying to guess that is to try and think of something that when I sub it in gives me 0. So let me just try some things. F of 0 is 0 cubed plus 2 times 0 squared minus 1, which is not 0, okay. F of 1 is 1 cubed plus 2 times 1 squared minus 1, which is 2, which is not 0. Okay. Let me try minus 1. So minus 1 cubed plus 2 times minus 1 squared minus 1, which would be, now minus 1 cubed is minus 1 times minus 1 times minus 1, which is negative 1. Minus 1 squared is just 1. And that is 0. So the fact that this comes out to 0 means the remainder, when I divide by x minus 1, should be 0. Which means it's possible to divide by x minus 1 without being a remainder. So it must be possible to divide this by x plus 1. So that means that x plus 1 is a factor. And so what I'll do is I'll divide by x plus 1 and see what I get. Now, just a second, I'm just going to have to put in a bit for the x. So x cubed divided by x is x squared times x is x cubed, x squared times 1 is x squared. I take that off. 2x squared minus x squared is x squared. There's still these things. X squared divided by x is x. X squared, so x times x is x squared. X times 1 is x. And then I take that off. So 0x minus x is negative x. So negative x divided by x is negative 1. And negative x, so just a second, negative 1 times x is negative x. Negative 1 times negative 1 is negative 1. Take that off, I get 0. It did work. And so therefore, x cubed plus 2x squared minus 1 is x plus 1, x squared plus x minus 1. And now that's a quadratic. If I want to factorise that, the quickest way is probably to figure out when it's equal to 0. Solve x squared plus x minus 1 equals 0. So I know that whichever x's make it equal to 0 are going to be in the factors. And so if I solve this is equal to 0, now I can't think of anything right now. So I'd normally try and think of two things that multiplied to give this and added to give that. That doesn't look very likely. And so I'm going to use the quadratic formula. So minus b, so normally you call this a and b and c, and you go minus b plus or minus the square root of b squared minus 4 times a times c over 2a. So that gives me minus 1 plus or minus the square root of 1 plus 4, which is 5, over 2. Okay, so x equals minus 1 minus root 5 over 2, or x equals minus 1 plus root 5 over 2. And I know that if those are the zeros, the factors will have to be x minus that. So factors x minus and x minus. And so therefore, the original polynomial, which was x cubed plus 2x squared minus 1, must be x plus 1. We already divided by that. X and x plus 1 minus root 5 over 2. And so I have fully and completely factorized it. Means if I want to draw that, I know that it has 3 zeros, which is this, and -1, and it goes up, down, up. So what have we got? Just to make sure we've got everything together here, we know that we can use the various features of the way the function is written in order to figure out what the graph looks like. So we can sub in any point. We know that if we sub in any x, it should give me the matching y, and that can sometimes help us to figure out features of the function. We know that if we put the y-intercept in, put x equals 0 in, it tells us what the y-intercept is. We know that if we find the x-intercepts, we have to factorize it in order to do that. And we've just discovered at the end that we know we can factorize it if you've got zeros. And we know, based on the degree being odd or even, how many turning points it might have and which way the ends will point. And we know, based on the coefficient of the biggest power, what the options are for which way up it is. And we also know, based on how it factorizes, how it meets the x-axis. And we can use all of that to sketch the graph, or alternatively to look at a graph and make a guess at what the polynomial is. We know we can add and subtract and multiply them, and we have this brand new process called Polynomial Division, which can allow us to divide them. And then we're also able to do remainders in that process, to be able to write it as nearly a multiple of something, and that loops back to factors to be able to do something. I do have one more thing to talk about on the algebra front, which is that technically, when I talk about factors, from this algebra point of view, well, constants don't really count as polynomials in the same way as everything else. Okay, you know, I've got x minus 4, that's a polynomial to x plus 1, and x squared plus whatever. What if it was just the number like 4? Now, it's a perfectly good function. You can draw y equals 4. But it doesn't really behave mathematically like the other things do. Because sort of everything's a multiple of 4, because you can just go, well, it's a quarter times 4 times whatever it is you want. So that starts to be a problem. Now, only some things can be written with x minus 3 as a factor, but everything can be written with 4 as a factor. So that means that we don't count constants when we talk about factors. So it's worthy to point this out finally. Factors, when we're doing this polynomials as objects. If you can write f of x is two things multiplied together, like that, then px and qx are called factors of f of x. And there might be lots of ways to write something as two factors. But if you do write it down with as small a degree factors as you possibly can, there's only a small number of ways to do that. Okay? So any polynomial can be written as a product of things like this, x minus a's, and or x squared plus ax's plus b's, and or a constant. Okay? That means that any polynomial has those factors. So, the problem is that the constant, well, I can do times a quarter, you know, and fiddle with it. And so we don't normally count constants as factors. Constant don't count. So if I had an example, and I said f of x has both x minus 5 and x plus 2 cubed as factors, and is of degree 4, what is f of x? Well, then we know that to get degree, we know we have to have both of these pieces multiplied together, and that's already going to be degree 4 because it's got 3, and then we'll times by an extra x, and that'll be degree 4. So we know that f of x is going to have to be this. But we know that constant multiples don't count as factors, and so there could be another constant there as well. It could be something times that for some a. And until I know what the a is, I can't tell anymore. So I'm just going to have to leave it. I do know that the a can't be 0, technically, because I mean, really, if it's just the 0 function, then that's a bit stupid. And I also know how to graph this as well, just to be sure. It has a 0 at 5, it has a 0 at minus 2. I know it crosses through at 5. And I know that it does what x cubed does at this point, which means it's actually going to do that. I didn't say that earlier because it just seemed like a lot of information, but if you happen to notice it, then that's fine. And it is facing the right, it's the right sort of shape for a quartic. Both ends are facing the right way. It has one turning point, that's okay. But it could just as easily be this way for a being positive, but it could also just as easily have been this way. For a negative. So if someone asked me to draw this graph, I would have to give both options because I don't know what the a is. Now, if I had a point on it, if I was told what the y-intercept was, then I could figure out what the a is, like I did in the earlier example. So that's polynomials, and really polynomials is the beginning of our understanding of functions. All functions are sort of polynomial shaped if I'm close enough to them. Some of them not so much, but most of them are pretty close. And having an idea of turning points and that sort of thing is going to help us when we get into doing calculus. And thinking about them as algebraic objects that allow us to do multiplication and division and whatever helps us to have the same ideas about new kinds of objects like matrices and vectors and that sort of thing later on. So polynomials are a really good place to begin your mathematical journey. Thanks for listening.